Hi everyone, this is Dr. GVR Seshagiri Rao, Professor in the Department of Mechanical Engineering, Institute of Aeronautical Engineering, Hyderabad. So we have discussed in the previous sessions about the theories of failures. So in this, in theories of failures, there are 5 theories. Already we have discussed 3 theories like maximum principal stress theory and maximum principal strain, and then shear stress theory. So, and another 2 theories are there. The theories regarding the strain energy. So, that's why those theories are called as strain energy theories. So, in solid mechanics and materials, we have discussed the simple stresses and strains and the relations between the elastic constants, and other topics, the shear stress and shear force diagrams and bending moment diagrams, and how to calculate and how to draw we have learned. And also we have learned the maximum principal stress and the principal planes and principal strains. So these theories related to the maximum principal stress and the principal strain relative magnitudes and then principal planes. These theories are developed to avoid failure, so that before designing any component, you should use these theories to avoid the failure and always for a safe design. So that's why in these theories, they derived the conditions for safe design. So what is the failure condition, and then how to avoid the failure? There are conditions are there. So already we have discussed in some conditions in our previous session. In today's session, so I want to discuss about strain energy related theories. So before going to enter the main topic, the student should know the outcome of this topic. So actually, in this, there are principal stresses and principal planes, and then calculation of principal stress and maximum principal stress and maximum principal strain, and also analytical methods and graphical methods like Moore circle and analytical methods, and theories of failures. So at the end of the topic, the student should be able to demonstrate the principal stresses and the principal planes and torsional stresses acting on in a arbitrary plane within a structure using analytical and Moore circle methods and theories of failure. So in this, the student should understand the principal stresses and the principal planes and the Moore circle methods, and already we have discussed. So at the end of this topic, they can able to answer all these things, demonstrate the principal stress, and also they can speak about the theories of failures. So already we have seen the theories in the previous session. So now the fourth one is the maximum strain energy theory. So what is this strain energy? So maximum principal stress and maximum principal strain and maximum shear stress already we have seen in a previous session. So the maximum strain energy theory, also known as Beltrami's theory or Higgs theory, is one of the criteria used to predict the failure of a material under complex state of stress. So this theory is typically applied in the context of material mechanics, particularly for ductile materials. For better materials, have seen in maximum principal stress theory, that is used for ductile materials. Brittle materials. The principal stress theory, the maximum principal stress theory, used for ductile materials. So the strain energy theory predict the failure of materials under complex states of stress. So this theory is typically applied in the context of material mechanics. So particularly the ductile materials. So that this theory is also known as Beltrami's theory or maximum strain energy theory. So in this, the main components are strain energy density. So strain energy is the energy stored in a material due to deformation under load. Suppose any object is subjected to load. So this object is subjected to tensile load. So what will happen? Due to this load, some deformation will be occurred. So after changing L and 1 and before L. So some strain energy is the energy stored in the material due to deformation under load. The strain energy density refers to the strain energy per unit volume of the material. So the density is equal to the strain energy per unit volume. The strain energy you can represent with U and the volume, unit volume. So here, like the under different states of stress means uniaxial and biaxial and triaxial. So the material experience strain energy due to elastic deformation. So you know elastic deformation. Up to elastic limit, the stress is directly proportional to strain within the elastic limit. So beyond this elastic limit, it occupies permanent plastic deformation. See, at this stage, within the elastic limit, whenever you remove the load, it regains its original shape. So due to load, it occupies some deformation. So that is not a permanent deformation. That is temporary deformation. Whenever you remove the load, then it regains its original shape. So that is called as elasticity property. So elasticity and plasticity, you know, these two are mechanical properties. So very, very important for material selection. In the case of plasticity, what will happen? The material, whenever you remove the load, does not regain its original shape. So it means it occupies the permanent deformation. See, so here under different states of stress, uniaxial or biaxial or triaxial, uniaxial two stresses, that is sigma 1 and sigma 2, and say in x direction and y direction, sigma 1 and sigma 2 or sigma x and sigma y. The biaxial only one state stress, triaxial 3 cases, sigma 1, sigma 2 and sigma 3. The material experience strain energy due to this elastic deformation. So that the strain energy density is very important in this maximum strain energy theory. So next, failure criteria. So the failure criterion is the maximum strain energy theory postulates the failure will occur when the strain energy per unit volume in a material reaches a critical value. So whenever this strain energy per unit volume, so that's it, density. So already we have discussed in the strain energy density. The strain energy density refers to the strain energy per unit volume of the material. So that the maximum strain energy theory refers to that failure will occur whenever the strain energy per unit volume in a material reaches a critical value. Then the component will fail. So this critical value corresponds to the strain energy when the material reaches its yield point in a simple tension, that is uniaxial loading. So whenever the component, the material reaches its yield point in simple tension, the standard specimen tested under UTM, Universal Testing Mission, in simple tension. So that is applying load is uniaxial loading. So whenever it reaches this point, yield point, the critical value will be obtained. So the corresponds the critical value is failure criteria. Whenever the strain energy per unit element material reaches this critical value, the component will fail. So mathematically, this theory compares the strain energy for a complex state to the strain energy under uniaxial tension. If the strain energy in the complex state exceeds the strain energy at the material's yield point, in simple tension or failure occurs. So if the strain energy in the complex state exceeds the strain energy at the material's yield point in a simple tension, so that is the failure criteria of the strain energy theory. So mathematical expression, the strain energy density in a material subjected to stresses, that is sigma 1 and sigma 2 and sigma 3, can be expressed as, this is triaxial loading, where the E is Young's modulus, mu is Poisson ratio, and sigma 1 and sigma 2 and sigma 3 are principal stresses. So principal stresses already we have discussed. You know the Poisson ratio and Young's modulus. So the mathematically the expression, so you can write like this: U is equal to, that is strain energy density, 1 by 2E multiplied with sigma 1 square, sigma 2 square and sigma 3 square, minus mu by 2E, sigma 1, sigma 2, sigma 2, sigma 3 and sigma 3, sigma 1. So in case of uniaxial, in case of biaxial, suppose in case of uniaxial, only the principal stresses sigma 2, sigma 1, sigma 2 will be active. So you can substitute the in place of sigma 3 0. So here sigma 3 0 and uniaxial, biaxial. So then uniaxial, sigma 1 and sigma 2, sigma 3 is 0. Biaxial only sigma 1, sigma 2 and sigma 3 is 0. So like this, you can write expressions for triaxial loading and biaxial loading and uniaxial loading. So according to the maximum strain energy theory, the failure occurs when the U is the critical value, reaches the critical value. Here U critical is the strain energy density at the yield point under uniaxial tension. The strain energy density at the yield point under uniaxial tension reaches its critical value. So what are the applications of this strain energy? So this theory is mainly applied to ductile materials. So where the elastic deformation is significant before yielding. So while this theory provides a general understanding, it's not the most widely used for design purposes. The von Mises and Teska criteria are more commonly applied, especially for metals. So in design of component, the material selection is important. And then, so what are the forces, loads acting on the component? You have to analyze and apply the theories. For understanding this theory only useful, the strain energy. The maximum strain energy, destruction energy theory is there. I will discuss in the next slides. So that theory is called as von Mises theory. So most probably the von Mises and Teska criteria is most commonly applied theory for designing of components. Clear? So that wherever the elastic deformation is significant before yielding, there this theory is applied. So in three-dimensional stress system, the strain energy per unit volume is given by, so the three-dimensional, so already shown in the previous equation. So here instead of here 1 by 2e take common and then write this equation sigma 1 square, sigma 2 square, sigma 3 square minus 2 mu. So use here mu in the Poisson ratio and sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. So u is the here sigma square by 2e per gradual load, that is strain energy, and then you can write the above equation, substitute in place of u sigma square by 2e and the remaining, the equation is same, the 1 by 2e into sigma 1 square, sigma 2 square, sigma 3 square minus 2 mu into sigma 1, sigma 2, sigma 2, sigma 3 and sigma 3, sigma. This is triaxial loading. These sigma 1 and sigma 2 and sigma 3 are principal stresses. These three are principal stresses. Clear? So now the three-dimensional stress system, the strain energy per unit volume is given by, so here substitute sigma square by 2e. So the equation you can write sigma e square is equal to sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma. Why? Because here u is equal to sigma by 2e. So actually the equation is u in place of u sigma square by 2e is equal to 1 by 2e into sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu sigma 1 sigma 2 plus sigma 2 sigma 3 plus sigma 3 sigma 1. So get cancel here 2e. So you will get this equation, sigma e square is equal to sigma 1 square plus sigma 2 square plus sigma 3 square minus 2 mu into sigma 1 sigma 2 plus sigma 2 sigma 3 and sigma 3 sigma 1. Suppose this is not a three-dimensional stress system, it's only say uniaxial. So then sigma 3 is equal to 0 for uniaxial. So put sigma 3 is equal to 0, substitute, you will get so you will get sigma e square is equal to sigma 1 square plus sigma 2 square minus 2 mu into sigma 1 sigma 2 plus sigma only sigma 1 sigma 2. So this is the equation for uniaxial stress system. Clear? So you have to write according to the dimensional stress system. So the actual design sigma e is replaced by the allowable stress obtained by dividing sigma e by factor of safety. The actual design, the allowable stress will be occur. So in three-dimensional case, two-dimensional case already I told you sigma 3 is equal to 0. So the equation reduces to sigma e square is equal to sigma 1 square plus sigma 2 square minus 2 mu into sigma 1 sigma 2. If sigma is the working stress in the material, the design criteria may be stated as follows. So what is the design criteria? So sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 less than or equal to sigma square. So if the sigma is the working stress in the material, so the actual working stress, the design criteria may be stated as follows. These are principal stresses. Always the principal stresses sigma 1 or sigma 2 or sigma 3 less than or equal to the working stress in the material. So this is for the design criteria. Criteria is shown like this: less than. Whenever this greater than the working stress, then component will be fail. So that is failure condition, and for condition for design, the condition for safe design is you have to write like this: sigma 1 square plus sigma 2 square minus 2 mu into sigma 1, sigma 2 less than or equal to sigma square. So the results of this theory are similar to the experimental results for ductile materials for which the elastic the stress at elastic limit is equal to the stress available at compression state. So next one, the last theory is the maximum shear strain energy theory. So this theory is called as distortion energy theory. So this theory is due to von Mises and Henke. That's why this theory is called as von Mises theory. So this theory is commonly used for analysis of components. So this theory is also known as distortion energy theory or shear strain energy theory or von Mises and Henke theory. So according to this theory, the failure of material occurs, the total strain energy per unit volume in the stressed material reaches a value equal to the strain energy per unit volume at the elastic limit in the simple tension test. Okay? So the failure of a material occurs when the total shear strain energy per unit volume in the stressed material reaches a value equal to the shear strain energy per unit volume. The total, here you are taking total. So in the previous case, that is maximum strain energy only. So we are using only strain energy per unit volume. We are taking here considering total strain energy per unit volume. So that is equal to the strain energy per unit volume at the elastic limit in the simple tension test. So the total strain energy per unit volume due to principal stresses sigma 1 and sigma 2 and sigma 3 in a stressed material is given as, you can write equation 1 by 12c into sigma 1 minus sigma 2 whole square plus sigma 2 sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So the C is here, you can see the modulus of rigidity. Okay. So see, suppose for uniaxial, here also same, take sigma 1 and sigma 2 and sigma 3 is equal to 0. Substitute sigma 3 is equal to 0. So we will get one more equation. So I will show you here. So at the elastic limit, the tensile stress in a simple test is sigma t star. Hence, at the elastic limit, the tensile stress in simple tension test, the principal stresses will be sigma t 0 and 0. In elastic tensile and simple tension test, only one stress is available. That is biaxial stress system. So remaining sigma 2 and sigma 3 are 0. So that the shear strain energy for a unit volume at the elastic limit in simple tension, the equation will be 1 by 12c into sigma 1 and sigma 2. In this case, the sigma 2 is equal to 0 and sigma 3 is equal to 0. In the equation C here, 1 by 12c into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So here in this case, the sigma 1 and sigma 2, sigma 2 and sigma 3 is 0. In this elastic limit, the tensile stress in simple tension test. Clear? So finally the equation you can write 1 by 12c into 2 sigma t whole square. Clear? So here, so now expand this one 1 by 12c sigma t square plus sigma t square. So 1 by 12c into 2 sigma t whole square. Clear? So you can write 1 by 6c sigma t square. So the maximum strain energy theory for the failure of the material, the condition is the 1 by 12C, the sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square is greater than or equal to 1 by 12C into sigma 2 sigma t square. So this is this stress is already we have calculated the strain energy per unit volume at the elastic limit in simple tension test, this value. So the for failure, this principal stresses, so whenever the maximum strain energy per unit volume is greater than or equal to this tension test stress strain energy, the component will fail. So the final equation you can write like this: sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square greater than or equal to 2 into 2. But to avoid failure, the equation for design purpose or for safe design, that is less than or equal to 2 sigma t whole square. So always these values should be less than the allowable stress values. So then only the component will be in a safe condition. So here see sigma t is equal to the allowable stress divided with the factor of safety for actual design. The sigma t is considered as the design purpose, the sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So is equal to 2 sigma t whole square. For two-dimensional stress system, sigma 3 is equal to 0. So already I told you. So the sigma 1, sigma 2, these two are available and the sigma 3 is 0 for two-dimensional stress system. Substitute sigma 3 value in 0 in the above equation. So you will get the sigma 1 minus sigma 2 whole square remaining 0. 0, 0. So now write the equation: sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is equal to sigma t square. So this is so design purpose the two-dimensional stress system equation. Clear? So write this like this. You have to write equations for two-dimensional or three-dimensional or the triaxial systems. In triaxial systems, so you get sigma 1 and sigma 2 and sigma 3. Three stresses are present and you can write the equation. Now final equation, the two-dimensional stress, sigma 1 square plus sigma 2 square minus sigma 1 into sigma 2 into sigma t. For biaxial, so for biaxial means only one stress, that is sigma 1 square, then sigma 2 0 and 0 is equal to sigma 2 square. So in this case, sigma 1 square is equal to sigma 2 square. So nothing but here that sigma t is equal to sigma 1. So that is the principal the stress is equal to the actual design, the sigma t. So in this session we have discussed about the strain energy theories. There are two theories. One is the maximum strain energy theory and another one is the distortion energy theory. So in this theory we have seen the equation, the mathematical expression with Young's modulus, and then the applications also we have discussed. So mainly applied to ductile materials where elastic deformation is significant. So and it provides for general understanding only. The one measures and test criteria is very important. So and then the three-dimensional stress system, the strain energy per unit volume equation also have discussed. And then the actual design the factor of safety we are using. So the allowable stress obtained by dividing the each sigma E by factor of safety, we will get allowable stress. So two-dimensional in case the sigma 3 is 0, the equation reduces to sigma E square is equal to sigma 1 square plus sigma 2 square and 2 mu sigma 1 sigma 2. So already we have discussed. And then the working stress in the material, that is safe design. The condition is sigma 1 square plus sigma 2 square minus 2 mu sigma 1 sigma 2 less than or equal to sigma square. So we have discussed. And then the maximum strain energy theory, shear strain energy theory. So that is called as distortion energy theory. So the theory is due to von Mises-Encke is called as the scientists derived this theory. That's why this theory is called as distortion energy theory or von Mises-Encke theory. So this, according to this theory, the failure occurs when the total shear strain energy per unit volume in the stressed material reaches a value equal to the shear strain energy per unit volume at the elastic limit in the simple tension test. Already we have discussed, and we have written the equation also we have seen. So the written equation is 1 by 12c into sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square. So same elastic limit and tensile stress in simple test taken here sigma t. So the shear strain energy per unit volume at the elastic limit, the simple tension test written equation like this: 1 by 12c into 2 sigma t whole square. Clear? And then the failure of material, the condition is shown here. We have discussed the sigma 1 minus sigma 2 whole square plus sigma 2 minus sigma 3 whole square plus sigma 3 minus sigma 1 whole square greater than or equal to. This is for failure criteria. For safe design, to avoid failure, it should be less than or equal to 2 sigma t square. And also we have discussed about design purpose equation for two-dimensional stress systems. In two-dimensional stress system, there is only sigma 1 and sigma 2 will be present and sigma 3 is 0. Clear? So that the terms sigma 3 terms are 0, and then substitute sigma 3, you will get the equation is the final the equation for two-dimensional stress. So we have seen here sigma 1 square plus sigma 2 square minus sigma 1 sigma 2 is equal to sigma t square. For biaxial system, you have seen here written only one stress will be present, that is sigma 1, remaining two stresses are 0. So that is equal to the actual design. So like this, how to write the failure condition and then safe condition for different theories. So all theories we have covered. So in this theories of failures, we have discussed about maximum principal stress theory, and then what is the condition for safe design we have seen, and then maximum principal stress theory, shear stress theory, we have seen the condition, and maximum principal strain theory, and also we have derived the condition for safe design, and then also we have seen failure design. So, and remaining two are strain energy theory, the maximum shear strain energy theory, and then maximum strain energy theory and maximum shear strain energy theory. These theories are very important while designing a component. So whenever you want to design in mechanical component, mechanical engineering, so these theories you should use. So according to the material and then the type of loading. Suppose the material is brittle materials. So the suitable theory is maximum principal stress theory. Your material is ductile materials, the maximum shear strain theory. So these theories applicable for according to the different materials and then the type of application. So the design engineer should remember these points, and according to the material selection and the loading, they should use these theories to avoid failures for and for safe design. So then only the design will be in a safe condition. If you not used proper theories and proper loading, then what will happen? Your component will be fail due to bad loading and due to not related theory or not used. Clear? So that for every engineer, for design component, for every design, the design engineer should follow and should understand these theories. So that's why the theories of failures is very important in design and also in subject solid mechanics and materials. So for this PPT, I have taken references are S. Ramamrutam, other name, and title of the book is 10th of Materials. So, and the publishers are Dhanpati Rai. And then R.K. Rajput, the title of the book is 10th of Materials. And publishers are Chand and Co., the New Delhi, Nation 2007, and R.K. Bansal, textbook of Strength of Materials. And then R.S. Kurmi and Gupta. The title of the book is 10th of Materials. So you can take latest edition also for reference. For you take any one reference and textbook for more details. So that these references I have taken for this PPT. Clear? Thank you.
Like, share and subscribe. Hit the bell icon for more updates.